Nature's most destructive presence is the thunderstorm. It contains every conceivable aerial hazard: destructive hail, catastrophic turbulence, vicious icing, violent wind shear, and explosive lightning. You must find thunderstorms and avoid them. Let's ask two pilots about radar or spherics. Our first pilot is a commercial pilot. Can radar equipment detect thunderstorms?
Well, not really. It detects water. It often confirms what you expect to find, and without expectation, it can be confusing. But to answer your question, can radar equipment detect thunderstorms? No, it detects a byproduct of thunderstorms, which is water.
Our next pilot is a corporate pilot. Can radar equipment detect thunderstorms?
Yes, radar can detect thunderstorms. The different shades of color on the radar screen indicates different levels of precipitation. The heavier the precipitation, the stronger the rainfall, the indication of a thunderstorm. I think that with skill, knowledge of the equipment and its limitations, and some operator experience, that the pilot can detect thunderstorms using radar.
The term spherics comes from atmospherics and means lightning detection. Can spherics equipment detect a thunderstorm?
Yeah, spherics can detect a thunderstorm. Since all thunderstorms have lightning, spherics equipment is designed to detect it.
No, it can't. Spherics equipment can identify areas of lightning strikes, but it can't define the diameter or the circumference of the storm. After all, we can get lightning strikes in volcanic ash, snowstorms, and even cloud-to-cloud changes the presentation on the screen.
Okay, now if you had one choice of either radar or spherics, which one would you choose?
I'd choose spherics. Wherever there's lightning, you know there's a storm. Plus, the number of lightning strikes and their location can give you a good idea of the size of the storm.
It's radar. With radar, you can see the formation of the storm and the areas that you want to avoid.
Although everyone may not agree on equipment preference, everyone does agree that no one should become a thunderstorm statistic. There are products that can help you avoid thunderstorms. But before we discover what's available and what it can do, let's assure that all of us concur on the definition of a thunderstorm.
A thunderstorm is a towering cumulus cloud heat machine fueled by water. Its power represents nature's most destructive presence, including tornadoes. The danger of a thunderstorm to pilots is both electrical and icing, but primarily the turbulence. It is the hazard within unstable air associated with the storm. Pilots should know of the characteristics of different types of clouds and what to expect when flying through them. In particular, two types of clouds should have meaning to pilots. One is stratus. These are usually low-level, layered gray clouds of minimal to moderate rainfall. They are not hazardous unless they surround and camouflage more hazardous towering cumulus clouds. Since clouds are water in vapor form, icing is a threat in clouds when temperatures are below freezing. Heat creates the dense white cauliflower clouds called cumulus. These are more prevalent in spring and summer months when the heat from the sunshine creates this uplifting air. As air lifts and cools, moisture in the air condenses, contributing to further cloud growth. With enough of this activity, you have a thunderstorm, and those are dangerous. Thunderstorms must be respected because of the damage they can cause. Some of the elements of thunderstorm danger include destructive turbulence, hail, ice, lightning strikes, and wind shear. Remember, 200-mile-per-hour tornadoes can come out of thunderstorms. To navigate safely in the vicinity of a thunderstorm, you should keep a 25-mile buffer between you and the storm. Any cloud mass suspected to be a thunderstorm should be considered hazardous, and all precautions taken to avoid it. Even in high-performance aircraft, it may be difficult to outmaneuver Mother Nature. If you don't fully comprehend the kind of weather that confronts you and the hazards in it, avoid it. Storm avoidance equipment provides the means to do that. Pilots have the two choices we've mentioned in selecting storm avoidance equipment: radar, and spherics devices. Each is sophisticated technology, but operates and detects quite differently. We'll examine each one in more detail, but you have to decide which best meets your needs for your aircraft in your flying conditions and for your budget. Radar is active, generating and receiving its own energy. It transmits a short pulse of electromagnetic energy and listens for a return of the pulse. When a traveling wave of energy strikes water, some of the energy reflects back to the radar receiver. The circuits in the receiver measure the elapsed time between the transmission and the reception echo to determine the distance to the target. Most thunderstorms contain large water drops and create heavy rain. Radar, a water detector, can locate and display the cells of water that thunderstorms typically exhibit. Thunderstorms in the western half of the USA are unique. They are called desert type or high plains. All of the destructive power is there, but the water is not plentiful. They may create a benign radar image, so experience and education in radar use is essential. There are many factors at play when trying to interpret a radar properly. Tilt control of the antenna is imperative. Incidentally, radars are tilt limited on the ground and at low altitudes. You can't get them high enough to see what you really need to see. Remember, radars only look forward. Aiming an antenna too far downward not only buries the energy in ground returns, but reveals only non-threatening low-level rain showers. Thunderstorms are cumulus clouds with vertical development. We'll tilt the antenna upward to analyze water present as high as 25,000 feet. When it comes to antennas, the bigger the antenna, the better. Radar range is only limited by the size of the antenna. The focus of the energy transmitted is a function of antenna size. In aviation radars, we have energy focused like a floodlight or a spotlight, depending upon your antenna. Small antennas enable only short-range detection. Big antennas create a spotlight effect. Obviously, you can see farther and in more detail with a spotlight. Big antennas with narrow beams have distance advantages. Your aircraft itself is the antenna limiting factor. Aviation antennas vary in size from 10 to 30 inches. Big airplanes carry them in the nose cone called the radome. Light twins have small radomes accommodating only a 10 or 12-inch antenna. How about a single-engine aircraft? Your only option is a wing-mounted pod containing a 10-inch antenna. With a 10 or 12-inch antenna, effective range is 80 to 100 nautical miles. Regardless of range options on the radar control panel, 320-mile range selections might be impressive to consider and might help sell radars. But you are range limited by the size of your antenna. Many radars operate with a 4-color analysis: green, yellow, red, magenta. The color green on a radar display means that the rainfall is below 1/10 of an inch per hour. It's a weak rain shower with no threat of hazardous weather. The yellow color means rainfall is 1/10 to 1/2 inch per hour. The storm is classified as moderate, and pilots should take appropriate avoidance measures. Statistically, convective yellow echoes have a 40% chance of moderate turbulence and a 2% chance of severe turbulence. There is no comfort, and there is a bona fide threat to be found in convectively created yellow returns. Avoid them. Red is an area to always be avoided. However, geographic location is significant in radar interpretation, especially if you're flying over areas that are tropical with a plentiful supply of heat and water. Rain showers alone can generate red and yet be non-hazardous. See why it takes experience to read radar? You might expect to see rain showers that are red but not hazardous in Florida. In Kansas, red represents a considerable amount of water vapor that has surged northward from the Gulf of Mexico. Remember, radar must be interpreted geographically. Consider red in a semi-arid area to always be hazardous. Convective activity with 2 inches of rainfall triggers the color magenta. This means what you see must be treated as a severe thunderstorm. Only a thunderstorm could produce 2 inches of rainfall. The National Weather Service defines a severe thunderstorm as wind gusts exceeding 50 knots, having destructive hail of 3/4 inch or larger, or a tornado. Not all radars have magenta. Some radars operate with only a 3-color presentation, using green, yellow, and red to interpret storm intensity. One of the most important preparations to using your radar begins in the pre-flight briefing. It is during this phase that you want to establish what kind of weather you may encounter during your flight. Oftentimes, a valid national radar picture can be obtained from the Weather Channel, online services, or a flight service station. Since the average life of a single-cell thunderstorm is 1 hour, you can plan your flight accordingly. A lineal linked array of cells is called a squall line. It is a narrow band of active thunderstorms. Often it develops directly ahead of a cold front in moist, unstable air. But it may also develop in unstable air far ahead of any front. The line may be too long to easily detour and almost always too wide and severe to penetrate. It often contains severe steady-state thunderstorms and presents the single most intense weather hazard to aircraft. It usually forms rapidly, generally reaching maximum intensity during the late afternoon and first few hours of darkness. The more knowledge you have about weather and its repeated patterns, the better decisions you can make as a pilot. Radar systems have been in aviation on land and in the air since 1938. With the progress of technology, an average radar system for an aircraft starts at $25,000 and sophisticated sets are over $100,000. Depending upon your aircraft model, its radome and panel space, radar installation may or may not be an option. As pilots, the more information we have in the cockpit, the better. But it's also up to the user of radar to become familiar with the equipment, know what it can do, realize its limitations. No one but you is responsible for obtaining product knowledge. Most radar manufacturers can recommend a seminar or training program on the use of the equipment. A second type of storm avoidance equipment is spherics. Simply, it is a lightning detector. It can detect electrical discharges associated with thunderstorms up to a 200-mile radius of the aircraft. Spherics equipment is passive. It listens for an electromagnetic signal with a receiving antenna. There's no transmitter. The antenna detects the electrical and magnetic fields generated by intracloud, intercloud, and cloud-to-ground electrical discharges, and sends discharge signals to a display processor. The processor analyzes, then digitizes the discharge signal into range and bearing displays. The device displays discharges as dots, X's, or lightning bolts that may appear grouped as storm cells or simply random strikes, depending on the equipment. The size of the cluster indicates the relative size of the storm area. Avoid flying into areas that are cluttered with markings, and you'll avoid thunderstorms. The speed with which the discharge points appear indicates the electrical intensity of the area. The more intense the storm, the faster the discharge points appear. Spheric systems typically display in 120 degrees forward view and 360 degrees surrounding view. In the 360 degree view, activity in front, beside, and behind the airplane can be viewed simultaneously. This omnidirectional view is particularly a safety asset on the ground, taxiing out, and viewing thunderstorm activity within 200 miles. Yet the pilot is not even committed to flight. Updates on spheric screens are continuous and data will be retained on the screen for up to 3 minutes. In more severe storms, older data will be removed in less than 3 minutes and will be replaced with current information in the 120 or 360 degree view. With a severe storm, the markings will be plentiful, clustered, and the update will be immediate. Spheric's equipment can only estimate distances. Based on studied and statistical lightning strength and characteristics, it positions markings based upon these estimations. Especially strong strikes can show up closer than the body of the storm, and then of course the weaker strikes might appear more distant, although the main body of the storm should be evident. For reasons about which science cannot agree, a thunderstorm acquires a positive electrical charge in its upper layers and a negative charge in its base. Also, beneath a thunderstorm, there is an invisible shadow of positive ions that tracks the cloud on the ground. When the electrical differential is sufficient, an electrical arc may occur. This typically requires a polarity difference of about 3 million volts per yard of insulating air. Lightning strikes occur frequently in the cloud and from cloud to ground as nature tries to neutralize this electrical imbalance. By definition, all thunderstorms contain lightning. When we have a towering cumulus cloud emitting lightning, we have a thunderstorm and all of its attendant hazards. Lightning is a natural electrical discharge in the atmosphere. Each discharge generates an electromagnetic signal. Everyone has experienced interference resulting from these signals, especially when using personal radios. Pilots with ADF equipment have seen the needle swing erratically from one lightning strike to another. Spheric's devices simply amplify it, showing locations to be avoided. This is welcome information as opposed to an irritating interference with most other electrical equipment. Storms with frequent severe strikes will often appear on the screen like a long, narrow arrowhead with the point extending toward the aircraft. This array of strikes is called a radial spread. In some of the newer Spheric's devices, the radial spread may not be present because of advanced algorithms despite distance limitations. The equipment is always accurate in azimuth or bearing. You can expect to pay at least $4,000 to $20,000 for Spheric's equipment. And remember, installation is an important factor to consider. Where should the antenna be mounted to be most effective? Where can it be installed on an aircraft so that it detects the least amount of the airplane's own internal electrical interference? Ideally, where it's noise-free and where it is oriented to detect a lightning strike. If not already emphasized, this equipment is extremely sensitive. Anytime you can increase your awareness of the skies and any hazard in them, it's value added for you as a pilot. Although storm avoidance equipment is not mandatory, it does enable pilots to make more informed decisions, decreasing their chance of becoming a storm-related statistic. There are several types of Spheric's products available on the market. Request and read the pilot's guides that come with each piece of equipment. The more knowledge you gain, the better. Look for courses or one-day seminars about Spheric's, how the equipment should operate. The ideal situation, of course, is to own both pieces of equipment, radar and Spheric's. Some equipment is compatible and can actually overlay one another. so that they can be read at the same time and on the same screen. As pilots, keep what's called a vision to avoid. Isolated thunderstorms are easy to see when there's a thunderstorm in your flight path. Use common sense and turn to avoid the thunderstorm entirely. Even experienced aviators use their eyes to seek out bright spots, blue holes, and escape routes. Such visuals may be confirmed by the images displayed on radar or Spherix products. Our three sources of storm avoidance are vision, radar, and Spherix. We see the weather, we see and evaluate the displays, and see avoidance paths and escape corridors. Confirm safety by all possible means. Regardless of your skills as a pilot, the best advice is to avoid all thunderstorms. Be aware of the different types of avionics equipment available to help you avoid storms. Plus, know their limitations. Thunderstorms can be lethal. Aviation equipment may be expensive, but life is priceless.
Now you've got the big picture on storm avoidance equipment. Let's ask some of those same questions again to see if any of the answers have changed. If given the option of selecting only one piece of storm avoidance equipment for your aircraft, be it radar or Spherix, which would you choose?
You know, I'd rather not have to make that decision. Ideally, I want both pieces of equipment. What one doesn't detect, the other one will, and vice versa. I'd really prefer flying with them both.
I agree. It's much better to have both pieces of equipment. The more information I've got, the better I can make a decision that maximizes my flight safety.
Pilots everywhere agree. Storm avoidance equipment is a must for any aircraft. All factors considered, both pieces of equipment, operating independently or overlaid together, provide a better picture of the weather you're dealing with. Using radar and Spherix can paint a clearer picture of what flying conditions to expect. Never underestimate the power of your own vision. If the skies look hazardous, they probably are. And much like defensive driving, always be sure to leave yourself an out. It's up to us as pilots to keep informed about the equipment and its capabilities. Regardless of our reasons for flying, business, or recreational, whatever we can do to increase the safety of our transportation services, that's what we should do. When it comes right down to it, storm avoidance equipment is your choice.